Right. So here, let's look at the objectives of Section 2. First objective is to describe the formation of waves and the factors that affect wave size. Second, explain how waves interact with the coastline. And third, identify the cause of destructive ocean waves. So this whole section is going to be about waves. Let's get started. So first of all, what is a wave? We're going to talk about this at great length when you are in physics. It's actually my favorite section because it's where you get to do music and sound and stuff. So we're just doing the ocean right now, sadly. The wave in an ocean, just like anywhere else, it is a periodic disturbance in a solid, liquid, or gas as energy is transmitted through a medium. Translate that, it just means it's when something goes bleh because energy passed through. I mean, I got a big brain answer and a bleh, so you can just find where you're comfortable in the middle of that. One kind of wave is described as the periodic up and down motion of water. One wave has two basic parts. It's got a crest and a trough. So the crest is the highest point of a wave, and the trough is the lowest point between two crests, right? So the period of a wave is the time required for two consecutive wave crests to pass a given point. Okay, so the wave height is the vertical distance between the crest and the trough of a wave, and the wavelength is the horizontal distance between two consecutive crests or between two consecutive troughs. It's very basic math, but you know, it's still math, so be careful with it. But the wave speed is going to be the wave length divided by the wave period. Okay? I mean, units of velocity are always a unit of distance divided by a unit of time. This one is just describing waves in particular. Okay, so let's talk about wave energy. So the longer that wind blows from a given direction, right, the longer the sustained wind is, the more energy is transferred from wind to water, so the larger the wave becomes. Because of their large surface area, larger waves receive more energy from the wind than smaller waves do. So large waves grow larger, smaller waves tend to die out. Okay? You've got the wind blowing on the water. It may make a little disturbance, but if it's small, then it can't collect as much, and so the wind might end up just not keeping the wave going. You get a larger wave, though, all of a sudden you've got more space for wind to blow on, and as long as the wind is blowing in the same direction fairly consistently, you know, like a trade wind or a westerly or something, then you might end up with a fairly substantial wave. So although the energy of a wave moves from water molecule to water molecule in the direction of the wave, the water itself doesn't actually move very much. It's not like water is traveling so much as the movement of the water is traveling, right? So, I mean, you know, like people doing the wave in a stadium. The wave travels around the stadium, but no one is running around the stadium. It's just that one little element in that wave bumps the next one and then it goes back, right? So we're just talking about a phenomenon transferring through, not a substance traveling. So as a wave moves across the surface of the ocean, it's only the energy of the wave, it's not the water that's moving in the direction of the wave. When I say that Caribbean water, there is a current moving up the east coast of the United States, like from the last section, that actually is water moving. But this is a wave, and a wave is just a disturbance in the location of an individual water molecule, like on the surface, right? Okay, hopefully that's clear. I'm going to move on. The water molecule within the wave actually moves in a circular motion because there's the up-down part, but then there's also the push-return part. So you end up with a push up, return down. It's a circular motion. So during a single wave period, each water molecule will move in one complete circle. As a wave passes a given point, a circle traced by a water particle on the ocean surface has a diameter that is equal to the height of the wave. Okay, so hopefully we're getting a good idea about what a wave is and what it isn't. and how they behave and how to describe it mathematically. It would be real nice if we could all, take a field trip to the beach or something, but that's kind of a no-no right now. So, sorry. So, because waves receive their energy from wind pushing against the surface of the ocean, the energy received actually decreases as the depth of the ocean, as the depth of the water increases. So the deeper you go, the less energy there is from the wind and in the wave. It's mostly on the surface. So the diameter of a water molecule circular path decreases as the water depth increases. The wave motion gets less and less the deeper you go. Below a depth of about 1/2 the wavelength, there's basically no circular motion whatsoever. So the waves themselves are mostly in or at or directly below the surface. Right, so let's talk about wave size. So fetch is not just something you say to your dog, it's also the distance that wind blows across an area of the sea to generate waves. So there's 3 factors that determine the size of a wave. It's the speed of the wind. Obviously, faster wind will put more energy into the water. The length of time that the wind blows. You might have a sudden gust of very strong wind, but if it's over immediately, then no sustained wave is built. The wind has to blow for a longer period of time to build up that wave. And last of all, of course, the fetch, how much area of the ocean is that wind blowing on. So the size of a wave will increase to only a certain height to length ratio before the wave collapses. Obviously, water is a liquid. You can't build a big wave out of it. There has to be some sort of balance between how long it is and how tall it is. You can't have like skyscraper waves. That doesn't make any sense. They need to be more spread out. Okay, so whitecaps. That is something that happens when wind blows the crest of a wave off. Okay, because whitecaps reflect solar radiation, they actually allow less radiation to reach the ocean because it's a little reflective patch on top of the water, and so that might actually have an effect on climate because it affects how much solar energy is able to get into the ocean to warm it up. So choppier water, more waves, may have more froth on top of it. That's the crest of a wave being blown off, so the water becoming a bit more turbulent. And that is called a whitecap. Right, so when you're getting close to the coastline, that's where we generally think of waves because, you don't spend a lot of time out in the middle of the ocean. Whenever you go to the ocean, you're at the edge of it. You're on the beach, right, on the coastline. So in shallow water near the coastline, the bottom of a wave can actually touch the ocean floor. The wave will touch the ocean bottom where the depth of the water is about half the wavelength. So if you've got a wavelength of water, let's say 10 meters, then if the water happens to be 5 meters deep at that point, that's like almost 20 feet, then the bottom of the wave is now touching the ocean floor at that point. This is where you get the behavior of waves on the coast that you're familiar with from being at the beach. So let's talk about breakers. The height of a wave changes as the wave approaches the coastline, and here's why. As the wave moves into shallow water, the bottom of the wave is slowed by friction. But the top of the wave isn't, so it continues to move at its original speed. Finally, the top of the wave topples over and forms a breaker, which is a foamy mass of water that washes onto the coastline. This is, not just when the wave is rolling, but when it's so compressed and too tall for it to stand up anymore that the top of the wave just kind of like collapses and rolls off. Okay, if you've seen like those really cool surfing videos where like the surfer's like inside of a tunnel made of a wave, he's inside of, well, I should say he's underneath the breaker. Okay. The picture that you're seeing should kind of show how this is working. As the wave is being compressed because it's getting closer to the coast, there's less depth for the wavelength to sit in. So as you have less depth, it's affecting the wavelength, it's compressing it. That's going to be making the wavelengths speed up. And, I'm sorry, wavelengths speed up. Make the wavelengths compress, and that's where you end up with breakers. Basically, the wave is able to be stable out in the ocean where there's enough depth for the whole thing to sit, but as soon as it gets close to the coast, the wave doesn't fit anymore, and it goes a little nuts and then collapses in a breaker, and then it, washes away your sandcastle. All right, next up, let's talk about refraction. We're getting into some other thing from physics here. Refraction is something that waves do, and I don't just mean ocean waves, I mean like sound waves and light waves. They all do that. So refraction is a process by which ocean waves bend directly toward the coastline as they approach shallow water. So the part of the wave that is traveling in shallow water is going to travel more slowly than the part of the wave that is still advancing in deeper water. This happens because waves tend to take shortcuts through slower paths. It's one of the reasons why light bends through glass and through water. It's a physics thing, so if you're curious about that, of course, I could answer your questions, but let's not get into something that we don't need to get into. The point is that the slower moving wave in the shallow water is going to kind of bend in towards the coastline. So the wave will gradually bend toward the beach and then strike the shore head on. You're not going to get a lot of waves that hit the beach at angles. They usually hit it straight on because they bent in towards it as they slowed down. Okay, now another part, maybe a less fun part about waves at the beach are undertows and rip currents. So water carried onto a beach by breaking waves is pulled back into deeper water by gravity. That's fair. Water is pushed up onto the beach as a wave, and then it falls back down into the ocean. It's pulled back by gravity. So this motion causes an irregular current because it's not constant. It happens with waves. It's called an undertow. The generally weak undertow is often confused with the more dangerous rip current. So a rip current is not exactly an undertow. It forms when water from larger breakers returns to the ocean through channels that cut through underwater sandbars that are parallel to the beach. Okay, so it is a more extreme version of a similar phenomenon. It's a larger breaker that is returning to the ocean through a channel. It's not just the wave collapsing back into the ocean. It's a larger wave that returns through a channel, and those are more dangerous. Okay, let's talk about longshore currents. We've had rip currents, we've had undertow, now we've got longshore currents. So a longshore current, that forms when waves approach the beach at an angle. Now, I mentioned that they tend to approach head on, but that is not always the case. Sometimes they do approach at an angle. And so longshore currents flow parallel to the shore. Okay? It's not a current running into the shore, it's a current running along the shore. Great quantities of sand are actually carried by longshore currents. As the current is moving along the coast, it erodes just like the bank of a river, and it can move a lot of sand. So these sand deposits form low ridges of sand called sandbars. Sandbars are caused by a current of water moving along the coast and moving sand along with it. So the last objective of this section had to do with destructive waves, and so they've finally arrived. Don't worry, not literally. I'm just talking about in the lecture. So the term that I think we're all familiar with are tsunamis. They are giant seismic ocean waves. So most tsunamis are actually caused by earthquakes on the ocean floor, although some can be caused by volcanic eruptions and underwater landslides. It's a lot of water pushed all at once by some large-scale geological event like an earthquake or a landslide or a volcanic eruption. They're commonly called tidal waves, which is unfortunately misleading because they have nothing to do with the tides. So we use the term tsunami to properly refer to the large wave of water that is caused by a sudden catastrophic geological event. Right, so let's talk about them as destructive forces. They have a tremendous amount of energy, right? So all of the energy of this mass of water is released against the shore, and they cause a great deal of destruction. So just think about like if there were a sudden seismic shift of tectonic plates underwater. So you might have something that's like hundreds of thousands or millions of square kilometers all of a sudden move just a tiny bit. That pushed an awful lot of water. Just think of the energy it would take to lift part of the ocean. So all of that energy put into water causes a wave, and as that wave is moving toward the coast, then the same thing happens that we were describing just with the small wind-generated waves. The wave is going to have a wavelength, it's going to have a speed, and as it approaches the coast, and half the wavelength reaches the bottom of the ocean floor, well, then you're going to have the wave length compress, and it's going to build up and have breakers, but there's so much energy that this is a lot more intense. So I know that we live on the, or near the east coast of the United States. In the middle of the Atlantic Ocean is a divergent boundary, so it's not like we have convergent plates constantly like clashing into each other and causing earthquakes like there are on the west coast. So we don't usually have to worry about tsunamis here where we live. So like thank goodness for that, but still it's good to know what to look for when they happen. They're usually signaled by the sudden pulling back of water along the shore. That's as the crest of the wave approaches, the beach becomes a trough. Anyway, just something to watch out for, you know, if you happen to be on a beach in a different part of the world. All right, so there is a visualization of refraction in waves. Hopefully you'll find it beneficial, so take a look at that.